Hello, and welcome to our discussion of the eigentheory of homogeneous Sturm-Liouville boundary value problems. To begin, we recall that a homogeneous Sturm-Liouville boundary value problem is a boundary value problem of the following form. The differential equation part is first derivative on the product p of x f prime plus q of x times f equals lambda times r of x times f on the interval a to b, where here p, q, and r are given functions, and lambda is a given real number, and f is the unknown function, the solution we want to find, coupled with the two boundary conditions, alpha 0 times f of a plus alpha 1 times f prime of a equals 0, for constants alpha 0 and alpha 1, and beta 0 times f of b plus beta 1 times f prime of b for another pair of constants, beta 0 and beta 1. More precisely, p is a continuously differentiable function, q and r are continuous, p and r are positive valued, q is real valued, so p, q, and r are all real valued functions, and lambda is a real number. The numbers alpha 0 and alpha 1 are not both 0, and the numbers beta 0 and beta 1 are not both 0. So at least one of alpha 0 and alpha 1 is non-zero, and at least one of beta 0 and beta 1 is non-zero. We will compress the differential equations part with the following notation. Define a differential operator S by S on F is first derivative on the product p of x times f prime plus q of x times f, and define the operator SR by SR on F equals 1 over r of x times s on f. So the ODE part, which is first derivative on the product p of x f prime plus q of x times f equals lambda r of x times f, that's really the same as the operator s on f equals lambda times r of x times f, and that is equivalent to the operator SR on f equals lambda times f. Now this certainly looks like an eigenvalue problem for the linear operator SR, and indeed it is. We have here the eigenvalue equation, SR on F equals lambda times F. And so we will say that a non-trivial solution F to the boundary value problem is an eigenfunction corresponding to the eigenvalue lambda, where lambda is that special scalar parameter in the BVP. Abstract eigentheory on inner product spaces tells us the following fact. If we can find a subspace D of SR contained in the continuous functions on A to B, and an inner product on the continuous functions on A to B, such that our operator SR from the domain D of SR into the continuous functions on A to B is self-adjoint with respect to that inner product, then we will learn a number of useful things about the eigenvalues and eigenvectors, or eigenfunctions, of the operator SR, if SR indeed has eigenvalues. One natural inner product for problems that involve derivatives is the L2 inner product, which here we'll read inner product of f and g with respect to L2 is the integral from a to b of f of x times the conjugate of g of x for functions f and g that are continuous on a to b. And what one often does when working with an operator that involves derivatives in the L2 inner product, one wants to pop the operator around from one slot in the inner product to the other, and so you integrate by parts a lot. What should our domain be for this operator SR? Well, we are not just interested in solutions to the differential equation part of the problem on the previous slide. We also care about solutions that respect the boundary conditions. So let's encode the boundary conditions into the domain. Let's put the domain of SR, D of SR, to be the set of all functions f in C2 of a to b, that is, all twice continuously differentiable functions f. This is a good place to start because SR takes two derivatives, so f should have at least two derivatives available. But we won't just use all twice continuously differentiable functions on a to b. We'll require those functions to satisfy the boundary conditions, alpha 0 f of a plus alpha 1 f prime of a equals 0, and beta 0 f of b plus beta 1 f prime of b equals 0. And you can check, due to the linearity of the boundary conditions and the fact that they're both equal to 0, that this subspace d of SR is in fact a subspace of C2 and also of the continuous functions. We will also use this same subspace as the domain of our operator S. So remember, we really care about the operator SR, which is a differential operator scaled by 1 over R of x. But sometimes we'll want to learn some things about the plain old unscaled operator S. So both SR and S will have the same domain of functions in C2 that meet the boundary conditions. So then the boundary value problem, as phrased in the previous slide, compresses quite nicely. We want to find a function f in d of SR such that SR on f equals lambda f. And so one thing we might ask is SR self-adjoint with respect to the L2 inner product? That is, do we have the inner product of SR on f against G in L2 equal to the inner product of f against SR on G for all f and G in the domain of SR? And the answer, unfortunately, is no. Let's start with something simpler. Let's look at the unscaled operator S. Then it is true that S is self-adjoint with respect to the L2 inner product when it has this domain d of S in the space of continuous functions on A to B. And how would you prove something like this? How do you prove that any differential operator is self-adjoint with respect to the L2 inner product? Typically, you integrate by parts. A lot. You use the boundary conditions to help kill off some of those boundary terms that naturally arise from integration by parts, and you use the fact that P and Q, which are two of the coefficient functions in the definition of the operator S, P and Q are real valued, so you can pass factors under the complex conjugate in the L2 inner product, and it all works out. Now, does this help with SR if you know that the operator S is L2 self-adjoint? Well, let's see what we can do. We'll take f and g in the domain of SR, which is the same as the domain of S, so all the boundary conditions are met. And let's calculate the inner product of SR on f against g with respect to L2. This, by definition, is the inner product of 1 over R times SF against G in L2. And that, by definition of the L2 inner product, is the integral from A to B of 1 over R of x times S on F at x times the complex conjugate of G. And since R is real, I can absorb R into the complex conjugate on G. So this is the integral from A to B of S on F at x times the conjugate of G of x over R of x. And that I recognize as the L2 inner product of S on F against G divided by R. Now S is self-adjoint with respect to L2. So this is the inner product of F against S applied to the quotient G over R in L2. Here's the unfortunate thing, though. S applied to the quotient G over R is not equal to 1 over R times S applied to G, which itself is equal to the operator SR on G because of the product rule, or the quotient rule if you like. So even though I have this nice expression, inner product of SR on F against G in L2 equals inner product of F against S on G over R in L2, even though I sort of popped the S over to the other slot in the inner product, that's not going to help me with regaining or reclaiming my SR operator in this last inner product. So what do we do in math? When the math doesn't work out the way we want, we change the rules. We are going to introduce a new weighted inner product. And SR will be self-adjoint with respect to this weighted inner product, which means we can still get the reality of the eigenvalues and the orthogonality of the eigenfunctions, just with respect to a different inner product. Namely, since the function R is continuous and positive on the interval A to B, we'll define a new map, inner product of F and G in L2R, and this will be the inner product of RF against G in L2, which is to say the integral from A to B of R of x times F of x times complex conjugate of G. And this map turns out to be an inner product on the space of continuous functions on A to B. And you will prove that in an exercise. So now we will calculate our desired inner product of SR on F against G with respect to L2R. And this, by definition, is R times SR applied to F against G in the L2 inner product. And what is R times SR on F? This is just SF. So I have now the inner product of SF against G in L2. And because S is self-adjoint in L2, this is the inner product of F against SG in L2. And if I multiply and divide by R, this is the inner product of F against R times 1 over R times S on G in L2. Now let's go to the integral formulation. This is the integral from A to B of f of x times the complex conjugate of r of x times s on g at x divided by r of x. Now r is real valued, and r also relates to s in a nice way. So I'll absorb this r into s, and I'll get the integral from a to b, f of x times the conjugate r of x, times now the operator sr on g at x. And then since r is real valued, I'll pull that r out of the complex conjugate and get the integral from a to b of r of x times f of x times the conjugate sr on g. And then I read this as the inner product of r times f against sr on g in L2. And that, of course, is the inner product of f against srg in L2r. So now I have what I want. I started out with the inner product of SR on F against G in L2R, and I got the inner product of F against SR on G in L2R. I was able to pop SR from one slot to the other. So my operator SR from the space D of SR into the continuous functions on A to B is self-adjoint with respect to the L2R inner product on these continuous functions. Consequently, the abstract theory we previously developed says that if SR has eigenvalues, they are all real, and the eigenvectors, or eigenfunctions, corresponding to distinct eigenvalues are L2R orthogonal. That's still a big if, though. Remember, we saw an example of an operator that does not have any eigenvalues. This operator was necessarily on an infinite dimensional space, because otherwise in finite dimensions everything reduces to matrices. But we will need to make some assertion of the existence of eigenvalues in the first place for SR. And indeed, that's the content of our next theorem, the proof of which sadly is beyond the scope of our class. Namely, we assert that the Sturm-Liouville boundary value problem has eigenvalues. They can be written as a countable set, which I'll write as lambda k indexed from k equals 1 to infinity, all of which by self-adjointness are necessarily real. And rather remarkably, you can order these eigenvalues in strictly decreasing order with lambda k plus 1 strictly less than lambda k, and the limit as k goes to infinity of lambda k equals minus infinity. Next, each eigenvalue is geometrically simple, in the sense that you can find a function phi k such that if f is an eigenfunction corresponding to lambda k, then f is equal to alpha times phi k. That is, any eigenfunction corresponding to lambda k is a scalar multiple of this one special eigenfunction phi k. Third, eigenfunctions corresponding to distinct eigenvalues are L2R orthogonal. This is what the abstract eigentheory told us. And written out, this means that if you have two eigenpairs, lambda k phi k and lambda j phi j, and k is not equal to j, then the inner product of phi j against phi k in L2R is 0. That is, the integral from a to b of r of x times phi j of x times phi k of x conjugate is equal to 0. And last, and this is kind of a surprise, I think, but a very nice one, the normalized eigenfunctions give us a very special representation for piecewise continuous functions on the interval a to b. Namely, if f is piecewise continuously differentiable on a to b, then you can write f of x plus f of x minus over 2. That is the average of the left and right hand limits of f at x. This average is equal to the sum from k equals 1 to infinity of the inner product of f with phi k and L2r divided by the norm of phi k and L2r squared times phi k of x for x strictly between a and b. And if this looks kind of like a Fourier series representation for f, both with the average of the left and right hand limits on one side and this sum of a special inner product against these special eigenfunctions phi k on the right side, that should feel familiar. It is indeed closely related to the Fourier theory. And here, of course, the L2R norm of phi k squared is just the integral from a to b of the modulus of phi k of x squared. So we have four really nice properties of the solutions to a Sturm-Liouville boundary value problem, namely that only special non-trivial solutions exist at discrete particular eigenvalues, that we have these reality of the eigenvalues and the orthonormality of the eigenfunction relations, and that we have the eigenfunction expansions for functions that are piecewise continuously differentiable. Some of these facts, as we said, we were able to prove just as a consequence of self-adjointness from the general eigentheory. Other facts would require more specialized proofs, like the actual existence of eigenvalues in the first place and the validity of this formula here in part 4, and we will simply take those for granted and not prove those in this course.